Today, let's go over a medium question that I just solved on my own. This one took quite a few tries, but I was finally able to do it, so I'm really happy about it. So let's go over it. So this one's called minimum operations to make all elements in the array equal. So you're given an integer array nums that has positive integers, and what you want to do is simply, for each number in queries, you want to get the absolute difference of the sum of, so for 1, don't care about the elements that are the same, and you basically do 3 minus 1, absolute value is 2, 6 minus 1, absolute value is 5, 8 minus 1 is 7, 2 plus 5 plus 7 is 14, and here you would do, so there's everything minus this, absolute value is 2, 4, 1, so 2, 4, 1 is 7, 8 minus 5 is 3, so 7 plus 3 is 10. So that's what you would do. So just to draw a picture, you have queries. So for 1, you want to do absolute value of 3 minus 1 plus absolute value of 6 minus 1, because we don't do 1 minus 1 because it's equal to it. And then absolute value of 8 minus 1. So that gives you 14. And vice versa. So pretty easy. Let's go ahead and do this, at least the brute force approaches. So let's iterate over queries from left to right. So left to right, and let's call this now. And for n in nums, if n is not equal to q, then now plus equal to absolute difference of n minus q, right? As we talked about, not equal to the current element, the absolute difference of the current element and those other different elements. So this is my initial approach, and then you can just append now. This technically works, but it's going to be too slow because this is n squared. So I really had to think and come up with another solution, which I was eventually able to do after a lot of trial and error. So I'm going to show you. So time limit exceeded. Okay. So since we already know what we want to do, that's a good head start. So now, if you look at the topics, you'll notice that this is a prefix sum and binary search. So if we want to find the elements that are not the same and the absolute difference, let's make some observations. So Q is 1 right now. So let's maybe sort the array, and then we can basically do a binary search to find where 1 goes, which is going to be, in this case, it's gonna go at 0, and then the next element that's bigger than it using bisect right is gonna be at 1. So what that means is we only care about the sum here, which basically means we want to do the right sum, which is 6 plus 8 minus 1 times 2. Or 1 second, let me see here. So we want to basically run a binary search, and we want to get 6 plus 8 because, well, let's think about what we want to do. So the bisect left is going to give you every element smaller, so we can just say if every element is smaller than this guy, then we can just do 1 times the length of whatever the left side is, because that's how many we're going to be subtracting from. So if, let's say, the left array is 3, 1, and 3, and then you have 5, then we're going to do 5 times 2 minus 1 times 3, because you always know that this is going to be bigger than the sum of this, right? And then vice versa for the right side. If you have 6 and you have 7 and 8, then you're just going to do 7 plus 8 minus 6 times 2. And because you know this is going to be bigger than this, because it's not possible because the length is 2, right? That's why we're doing 2. And then if you add those together, then that gives you the sum of the absolute differences of all the elements that are not including the current one. So I'll show you in more detail what this means, but essentially what we have to do is let's sort nums and let's create a prefix array to get the prefix sums really quickly. Did I spell that right? Okay, cool. So let's iterate in queries now, and let's do a left. Well, let's do a left is bisect left inside of nums, because nums is already sorted. So we have 1, 3, 6, 8, and let's do q, and right is bisect right inside of nums q. So let's print left and right. Cool. So 0, 1. What this means is that first of all, we want to exclude everything from here and then get the sum of this. So here, for example, for 2, 2, that's just going to be the sum of everything, right? Or 2, 2 means the sum of everything up to, not including 2. So this takes a little bit of playing around with, but if you make some observations, you'll notice that, again, if left is bigger than or equal to 0, or is bigger than 0, that means that, well, this is the prefix part, so we can, if left is bigger than 0, then we actually have to subtract. Otherwise, if left is 0, then we just take the the prefix of, let's say, 1, 4, 10, 18. If left is bigger than or equal to 0, then we do 10 minus 1. Otherwise, if left is 0, then we just do 4, because that gives you the prefix sum of everything up to that point. And so if left is bigger than 0, again, because we know the current element, let's just say q, so you can see. And let's actually make this easier. Let's say left is nums of up to including left, and right is nums of right to the end. Let's print this. I just want you to visualize it better. So as I said, this is why we do 5 times 2 minus the sum of this, and then the sum of this minus 5 times 2, because that's going to give you the absolute difference between every element minus this in absolute difference, because again, you know this is bigger than this, and then this is bigger than the left side. So if left, or because this is going to get time limit exceeded, so if left, then we can do, let's say high is just going to be q times length of left, right? 5 times the length of 2. And then the low is just going to be sum of left. And then we can just call this first is high minus low. If right, this list is not empty. In this case, this list is be empty, so this would not execute. Then the high would just be the sum of right, and then low would be q times the length of right. Second equals to high minus low, then result.append first plus second. So, okay. Or we can just say now plus equal to first, now plus equal to second, because if this block is not true, then it's just going to stay as 0. So this technically works, but again, this is really slow because this is O of n, 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 this is O of n too. So even though you're using binary search, that's not going to solve the problem. That's why we're going to use prefix arrays to fix this. So the sum of left, as you know already, in this case, if left is not none, that means that we actually have elements. So if left is bigger than 0 and right is less than length of nums, then this is possible, right? This array, both arrays, well, we're just evaluating the conditions separately. They have elements in them. So then it would just be q times L, because L is the index up to the current point, minus 0 is just whatever it is. And then low would just be P of L. So, okay. Okay. Left. So again, just simplifying this a little bit. Now it's just about optimization. Okay, so highest sum of right. Length of right you can just do is going to be length of nums minus right, because it's everything from right to the end. So the total length minus the index right. Yeah, so let's call this n is length of nums. I don't know if that's going to help though. And then we're just going to use prefix sums to do these, get rid of this. So instead of this, just sum of nums up to left, sum of nums right to the end, right? Okay, so let's do list n. So first of all, we can make this a little better, which we're going to do by, so it's just going to be P of left minus 1, right? That's how prefix sums work, because if you want to get the everything up to this point, then it's just going to be the index minus 1. 25, a little better. Now we have to take care of this, which is going to be a little bit tricky because, so for example, what I was talking about was if you have an array 1, 2, 3 and you want to get the sum of this subarray, it's just going to be this number. For high, let's say if right is less than or equal to 0, then high is just going to be P of right minus 1. Otherwise, if we actually have right, then it's just going to be, high is just going to be P of negative 1, which is just the total sum, minus P of right minus 1. Hopefully that'll make it better. So it's O of 1 now, and there you go, passes all test cases. So that's the power of the prefix sum. What I meant to say was that let's say you have an array of 1, 3, and 5, and then 6, 8. If the right is everything, like it's less than or equal to 0, then the whole thing is just considered, every prefix sum is considered. Like if right is at 1, then you just give it 18, because 18 is the sum of everything, right? Otherwise, if right is actually not on, is past the 0th index to the right, then you do the 18 minus 1 to get the sum of this, for example. So 6 plus 8 plus 4 is 17, 6 plus 8 is 14, plus 3 is 17. So quite a tough problem, has a pretty low acceptance rate, but if you really play around with it and you really think about it and you really understand binary search and prefix sums, you can make it work. So thank you for watching and stay tuned for more.